Alright, here's our video today. Why the sun is yellow. And from the picture, it doesn't look yellow, right? It looks white, and sometimes the sun could appear white in the sky, especially when it's overhead. And we'll talk about that in the video. In actuality, the sun in space is white. It looks white from space as all stars do. It's when the electromagnetic spectrum of visible light enters our atmosphere, and you know this, when the light bends, it forms all kinds of colors, and we'll go over that. So we should write down, find my pen working, let's see. The sun appears yellow, and sometimes it appears white in our atmosphere. That's why we call it a yellow dwarf. The sun is a yellow dwarf. So the sun emits, and I said this before, electromagnetic radiation. It's basically light, and in all forms, because there's radio. Radio is a form of light, and the sun will emit a very small percent of radio, which is light. Microwaves are light. We can't see them. Then there's infrared. And the sun emits a lot of infrared, probably close to 50% infrared. And then there's visible light. I'll just put VL, visible light. Of course, I'm running out of room, so I'll bring them down here. And then after visible light, there's ultraviolet. We'll say UV. Then, of course, there's X-ray. Everything I'm writing here is light. They're made of photons. So, and of course, the sun will emit a very small percentage of gamma and X-rays, and these are dangerous. And it does emit UV, and we need UV, especially for vitamin D. And visible light is close to maybe 40, maybe 45%. So all the rest is the other part of the electromagnetic spectrum. So for this video, we're only concentrating on visible light because all we see is visible light. Birds can see ultraviolet light, and snakes, for example, and mosquitoes can see infrared light. But for us, visible light. So when the light from the sun, those photons, enter the atmosphere, they will scatter. So let's get a clean page. Now the scattering is called Rayleigh scattering. I'll just write this down. Rayleigh scattering. So, and we're talking about visible light now. So when that visible light enters the atmosphere, blue and violet scatter the best. So that's why the sky is blue. Well, the sky is not violet for a couple of reasons. The sun emits more blue light than violet light, number one. And number two, we're more sensitive to blue light than violet light, so we see the sky more as blue. Now, the reason why blue and violet scatter the best is because blue light has shorter wavelengths. So when you look at visible light, and here's the visible light, we have the red, which has the longest wavelength, and we have violet, which has the shortest. We have blue over here, and so forth. So these two are scattering, and of course our eyes pick up the blue because we have blue cones in our eyes. Again, our eyes are more sensitive to blue light. And the sun emits more blue light than violet light. And so when the blue light scatters, creating this blue sky, what's left is the yellow, orange, and red lights, and so red wavelengths, and they're more prominent. And so when we're looking at the sun, and we shouldn't look at the sun, but when we're looking at the area near the sun, it appears yellow because those are the wavelengths that didn't scatter as much as blue. So in other words, we can say that the scattering of the blue and the violet, and we'll just concentrate on blue, the scattering leaves the longer wavelengths again, yellow, orange, and red, the longer wavelengths, more prominent when we look at the sun and don't look at the sun. But we all glance at the sun. The thing is also, though, during midday when the sun is directly overhead, it doesn't appear as yellow, it appears more white because the light is traveling through less dense of an atmosphere. As you get closer and closer to the ground, the atmosphere is more dense. So when the sun is lower in the sky during sunrise or sunset, the light is passing through more of an atmosphere, increasing the effect of red and orange. So the angle of the sun, we should write down the angle of the sun, because of the density in the atmosphere, plays a role in whether it looks yellow or white. And again, some people have asked, well, if the wavelengths are the ones that are left are the red, orange, and yellow, how come we see it as yellow? Well, our eyes are more sensitive to yellow than red, and yellow has a more pronounced wavelength. Well, not a pronounced wavelength. Red is longer than yellow. Yellow in itself scatters better than red. And if you're wondering about green, well, green has scatters better than yellow, but green is kind of mixed in with the blue because the blue is scattering the best. And so somehow the green gets blended in. So we don't see a green sky, but occasionally you can see a green streak in the sky, and we don't see a green sun. And just to reiterate this, our eyes are more sensitive to yellow and blue light than green light anyway. Now, this is not why the sky is blue video, but the sky is blue because of Rayleigh scattering, because of the blue light scatters the best in our electromagnetic spectrum. And from here you can see, now the sun's right about here, as you know, we can say, let's say this is noon. Well, we should use blue, shouldn't we? Right, so this is where all the blue light is scattering. And so the longer wavelengths of red, get red going here, and red and orange, they appear toward the end of the day or toward the beginning of the day. And of course, if I can get orange going on here, it's also red and orange. So that's why at sunrise and sunset you do see more of an orange sky based on this picture. All right. So here, you can see a yellow sky, a kind of a white sun with a yellow aura around it. So again, this could be like maybe you're out in the West Coast and it's morning in the West Coast, and so in New York it is noon, let's say, and it's all the blue is scattering in New York, and then in the perspective of where we are in California, let's say we were in California or anywhere out west, then we have the other wavelengths reaching us, the yellow and the red and the orange. And of course, that's why we see that in the sky. Of course, this could be dawn, this could be dusk. Either way. Another way to think of it is as the blue light scatters, what is left on the edges is the yellow and the orange and the red. So again, just to review, the sun appears white or it appears yellow from Earth. We know in space it is white. It looks white in space. But as the light from the electromagnetic spectrum bends on our atmosphere, it looks either yellow or white. And the reason for that is because of, again, the scattering, the Rayleigh scattering I talked about, where the blue scatters very effectively and quickly, leaving the longer wavelengths more prominent. All right, that's our video today.